A rational number is any number that can be expressed as a ratio or fraction of two whole numbers. Similarly, a rational function is any function that can be expressed as a fraction of two polynomial functions. In this chapter, we'll be focusing on splitting rational functions to simpler parts, such as quadratic terms to linear terms, converting improper rational functions to proper rational functions, finding the line of asymptotes and turning points of rational functions, finding the modulus of rational functions, and most importantly, sketching the graphs of rational functions. As for this video in particular, we'll just be covering the very basics. To start off, let's look at the most basic proper rational function of 1 by x. Now, I know. Technically speaking, the most basic function is the constant c, but let's not deal with anything that won't be useful for us. So 1 by x is our de facto most basic proper rational function. It's a rational function because it's a fraction of polynomials of degree 0 and 1, and it's a proper function because the numerator has a highest power that's lower than the highest power of the denominator. This is what the graph looks like, but I'm sure you already knew that. We still need to break it down for the sake of our topic. If we follow the bullet list from the start of this video, we can see that this graph has no turning points and has two lines of asymptotes, x equals 0 and y equals 0. In sketches, we exaggerate this by drawing the graph like this. But what if we adjust this function a little? Say we make this 2 plus 1 over x minus 1. If you're familiar with how function displacement works, you should know that this curve is shifted 1 unit to the right and 2 units up, which also means that the asymptotes have shifted along with it. The vertical asymptote has shifted to x equals 1, and the horizontal asymptote has shifted to y equals 2. Now, if you look at the pattern here, you'll notice that the vertical asymptote is just the negative of this number, and the horizontal asymptote is just this number right here. For those of you who just want a shortcut to figuring this out and not bother with the logic behind it, just know that the vertical asymptote is the value of x for which the denominator equals 0, and the horizontal asymptote is the value of y for which the entire proper fraction converges to 0. Emphasis on proper, because if you take the combined function, you're just forcefully assuming the asymptote to be y equals 0. The longer explanation for those of you out there requires us to first define what an asymptote even is. The simplest definition you're familiar with is that an asymptote is a line that the curve approaches but never touches. And this is fine if you're in high school or whatever, but for this chapter we'll have to add more conditions over here. A more proper definition would be to say that an asymptote is a line that a curve continuously approaches but never touches as it tends to infinity, or negative infinity. That it refers to the curve which lies in 2D space, meaning we're considering the tendency of both x and y approaching infinity. Here, for the graph of y equals 1 by x, we see that the curve approaches y equals 0, which is the x-axis, as x tends to infinity. Similarly, we also see that the curve approaches x equals 0 as y tends to infinity. This also applies in the negative direction. But you probably noticed another word I added, continuous. What's that about? While it's easy to say an asymptote is a line that a curve will never intersect, that assumption is completely false. Yes, you heard right, it is possible for a curve to cut an asymptote, and the answer for why, you'll have to stick around for future videos. For now, let's just stick to the basics. Getting back to our second example, we can see that the vertical asymptote is the easiest to solve. All we need to do is figure out a finite value that x approaches for which y approaches infinity or undefined, which is why we simply equate the denominator to 0. As for the horizontal asymptote, we need x itself to approach infinity, and because of that, this denominator becomes larger and larger, resulting in this fraction becoming smaller and smaller, eventually converging to 0, leaving us with just 2. Thus, the horizontal asymptote is y equals 2. The exact same logic applies to every single rational function that looks like this. The vertical asymptote would be x equals c by b, and the horizontal asymptote would be y equals d, and a just being there, I guess. Go ahead, try it out. Actually, try these out. Pause the video now, because the answers will be revealed in 3, 2, 1, boom. Moving on, you'll be happy to know that even if I bump up the difficulty a bit, the steps you'll need to follow doesn't really change that much, at least when it comes to finding just the asymptotes. Let me explain. Let's start with the vertical asymptotes, since they're the easiest to find. All you need to do to find it is to equate the denominator to 0 and finding the roots. This applies no matter what degrees polynomial you have, but only if the polynomial can be factorized to linear functions. So if you can represent a function like this as a function like this, you have two asymptotes, x equals 1 and x equals minus 1. Keep in mind that the factorization of the denominator doesn't necessarily have to give you values that are integers. So a function like this will still give you valid asymptotes. Heck, even irrational values are acceptable. What isn't acceptable, however, is imaginary values, such as what this function would give us. So as long as this condition is fulfilled, you can have any kind of polynomial in your denominator, and you'll have the exact same number of vertical asymptotes as the highest power. Feel free to test it out on a graphing software. With that said, we still have several questions left to answer, such as, how do I even sketch a curve that has two vertical asymptotes? And what about the horizontal asymptotes? And also, what the heck is that continuity about? The short answer to the first question is differentiation. The long answer for this, and also the other two, would have to wait for future videos, so stay tuned. To summarize, we got to know what a rational function is, what a line of asymptote is, how to identify which part of a rational function corresponds to the vertical and horizontal asymptotes, and how to figure out what the vertical asymptotes are for any kind of rational function. As always, thanks for watching and hope this all helps. See you next time.